Okay, so welcome to section 3.4, which is graphing polynomial functions. So graphing polynomials. And I'm going to try something different now. I'm just going to, instead of writing it all out beforehand, let's just do it on the fly. So let's recall. The graphs of x to the first power. This is linear, right? If I have the graph of x to the 2n, which is odd, then this is parabolic or quadratic. So parabolic, that's the graph of a quadratic, is a parabola. And if we have, what color should I use now? We have x to the 2n plus 1, meaning an odd exponent other than the exponent 1, then this will be S-shaped, right? S-shaped. So let me reiterate: a line, a parabola, oops. Nope, it's not. Oh my goodness, kitty. There we go, a parabola. Or an S-shaped graph. Okay, so these are the standard graphs for polynomial functions. Remember, polynomials have integer, meaning whole number, exponents. So, definition. So let f of x a polynomial function have a factor of x minus a to the n. Then we have the following. Number one, n is the multiplicity. The multiplicity of number two, the root of x equal to a. Okay, so for example, so determine the roots and multiplicities, the roots and their multiplicities, for the following. Okay, so number one, let's say we have that f of x in factored form is 3 times the quantity x minus 2 to the 5th times the quantity x plus 1 to the 8th. Okay, so what are the factors we have here? We have a factor that can be set to 0, so we have a factor of x minus 2 to the 5th. So 5 is the multiplicity. Multiplicity is equal to 5. But what is the root? The root is the value of x that makes this 0. So do you agree that 2 minus 2 is 0? So the root is 2. The multiplicity is 5. So the way we say this is 2. 2 is a root of multiplicity five. Another way to state this would be the multiplicity of the number 2 is 5. Okay, so now let's look at the other factor, which is x plus 1. This has x plus 1 to the 8th. So I claim in this case, what colors should I use? Do I have other colors? Let's make this a bit darker. So in this case, I claim that the multiplicity here, multiplicity, is going to be 8. However, the root in this case, what value of x is going to make x plus 1 equal to 0, and that would be -1. So the way we're going to say this then is that the multiplicity of -1, that's the root, is, what's the power? The power is 8. So the multiplicity is the power on each distinct factor. Okay, so number 2, let's say we have that f of x is equal to x squared times x plus 3 times x minus 7 to the, what shall we do, 11th? That sounds good. Okay, so now we actually have 3 factors. So x squared. X squared is a factor. So this implies the root, what makes x 0 is 0, and the multiplicity. So therefore, let's use symbols from our sheet, therefore, the multiplicity of 0, meaning the power on 0 is, what is the power on 0 here? It's 2. That's the multiplicity of the root 0. Now let's look at x plus 3. So x plus 3, and that's to the first power, right? So this is a root equal to what? Well, what makes x plus 3 0? That'd be -3 plus 3. So therefore, we can say the multiplicity of the root, in this case, -3, is going to be the power on that factor. The power is 1. So the multiplicity of the root -3 is 1. So now let's look at the factor x minus 7 to the 11th power. So this implies that the root is going to be 7, right? Because 7 minus 7 is 0. So therefore, the multiplicity of the root 7 is the power on that factor, and the power is 11. Okay, do you know what I should have done? Is I should have annotated what the shape. 5 is S-shaped, right? That's going to be S-shaped. But I guess we'll come back to that. Maybe I'll just leave that for a moment. Okay, so let's do one more. Number 3, third time's a charm. Let's do f of x is equal to 72 times the quantity x minus 5 to the 9th. So there's only one factor here, and the factor is x minus 5. 72 can never be equal to 0. So we have x minus 5 raised to the 9th power. So what this means, is that the multiplicity of the root, so the root is 5, because 5 minus 5 is 0, is equal to the power on this factor, which is 9. So there we are. That's what multiplicity means. Okay, and let's also recall a couple things. So recall. A polynomial of number 1, even degree or even power, even power is parabolic. Overall. So I should say overall parabolic, meaning the end behavior is parabolic. So maybe I should say that. That sounds better. In which case I'll need more room. So let's move this down here. So even power implies overall parabolic. End behavior parabolic. What do I keep on saying? End behavior parabolic. But if it's not a monomial, it'll do weird things in between. And similarly, an odd power, if it's not just the power function, it's going to have end behavior that's S-shaped. Except for the first power, right? So let's call that number 3. Degree 1. So if the power is just 1, this is linear. Period. There is no variation. It is just linear. Let's also recall. Maybe I'll do this in purple. So recall. That the y-intercepts are at x equals to 0, whereas the x-intercepts will be at y equals to 0. Okay, so given all of that, let's note. So note. The graph of a polynomial function is, number 1, linear. Near a root of multiplicity 1. Number 2 would be S-shaped, or maybe I'll do parabolic for number 2. Parabolic near a root of even multiplicity. And number 3, it's S-shaped near a root of odd multiplicity. Near a root of odd multiplicity. So what do I mean by that? Well, let me show you. So for example, plot the following polynomial functions. Polynomian? No, not polynomial functions. Okay, so number 1, let's plot f of x is equals to, let's do x to the 5th times x minus 3 squared times x plus 2 to the 1st. Okay, so first let's look at our roots. So we know that the multiplicity of 0 is 5, so that is going to be S-shaped. because it's odd, right? The multiplicity is 5. Now let's look at the factor x minus 3. So the multiplicity of 3 is going to be 2. That's the power on that. So that implies parabolic. Do you know what? Maybe I should write these, rewrite f of x so we can see where I'm getting this. So let's do this. So f of x is equal to x to the 5th times x minus 3 squared times x plus 2. So now we can color code them. Maybe that'll help a bit. So if we have x to the 5, this implies the root is 0, right? So let me move this. Root is equals to 0. And we know that the multiplicity of 0 is the power, which is 5. Let's do the same for the other factor. So we have x minus 3, quantity squared. This implies that the root is positive 3, which means that the multiplicity of positive 3 is the power, or 2, so it's parabolic. Let's look at the final factor, x plus 2 to the first power. So this implies that the root is going to be negative 2. It's whatever makes that factor 0. So this means that the multiplicity, it's a terrible arrow. So the multiplicity of negative 2 is the power on that factor, which is just 1. So 1 is going to be linear. But before we move on, we need to find the overall degree. So overall degree we just add each of the exponents on each of the factors. So we're going to have a degree, multiplicity of 5 on the first factor, a multiplicity of 2 on the second factor, and a multiplicity of 1 on the third factor. So overall, we have a degree of 8, which is parabolic, right? So this is going to be end behavior, parabolic. Okay, so what else do we know? We know that the x-intercept is, well, when x is 0, y is 0 because of this first term. So that's nice. So let's go ahead and plot this. So x and y coordinate axes. Since there's no negative in front, it's parabolic going uphill. So what does that mean? So let's do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the first thing, I have a root at 0. The next one, I have a root at positive 3. And the next, I have a root at negative 2. Okay. 2x and y. Okay, I know that the end behavior is parabolic, meaning it'll be something like so at the end. Okay, so what that means is that I go from left to right in reading direction. I'm going to come down and I'm going to go through the root from top to bottom as a little line. So let me zoom in and make this a little line. That means I will be turning around and coming back up to the root at 0, which is going to be S-shaped. So it's going to be something like so. Then I'll be turning around and going back down to the root at 3, which is going to be parabolic. So it'll be a little parabola here at 3. Or maybe Let me make this a little better. Okay, so now I can connect the dots. Move this a bit more in line with where it is. So the overall graph will look like, actually let me just do this, and maybe I'll do it in gold. I want it to be different enough, so it's going to go down here as a line, going to come back around here to my little S-shaped graph. Then I'm going to connect these in a nice smooth, I'll try to at least. Something like so, and then something like so. So we can see that this is definitely has at least degree 4, because I have, what color was that? Boy, why can I not draw this well? Okay. Okay, so remember the turning points? So let's look at those for a second. Looks like I have 1, 2, 3, 4, 5 turning points. So I have 5 turning points. So the degree of this polynomial is at least 6. And it is at least 6 because it's 8. So it's more so. Now you don't have to do that on yours. I just wanted to show you that. Okay, so let's plot another one. So number 2. Number 2 here. So let's plot f of x is equal to, let's do x plus 1 quantity cubed and x minus 2, and then x minus, what shall we do? Minus 1 quantity squared, which is simple enough. Okay, so let's look at this function. So we have that f of x is equal to, we have the first factor is x plus 1. His multiplicity is going to be 3. Then we have a factor of x minus 2 to the first power. Then we have a factor of x minus 1 squared. So for x plus 1 cubed, this implies that the root is negative 1. And we see that the multiplicity of negative 1, which is the power on negative 1, is going to be 3. So that's S-shaped. Now let's look at the factor x minus 2 to the first power. So this means that the root is positive 2. And that means that the multiplicity of the root positive 2, which is the power, is 1. So we know that that's linear. And last but not least, we have x minus 1 quantity squared. So the root in this case is positive 1. And we see that the multiplicity on this root, positive 1, is 2. So we know that a multiplicity of 2 is parabolic. But before we can draw those, we need to know what direction we're coming from. So let's look at the degree. So the degree of the whole function. So maybe, did I put overall degree? Yeah, I put overall degree. Let me write overall degree. So we know that it's a degree of f of x, not just his factors. So overall degree, I'm going to sum the degrees. So what do I get? I get 3 plus 1 plus 2. So 3 plus 1 plus 2, that's 6. So once again, it's going to be overall parabolic. So end behavior will be parabolic. Okay, so now the intercepts will be different. Let's consider the y-intercept at x equals to 0. So if x is 0 in this function, what do we get? We're going to get that f of 0 is going to be 1 cubed times negative 2 to the first times negative 1 squared, because all of the x's are 0. So what that gives us then is going to be 1 times, so it's negative 2. So my y-intercept is at negative 2. And the x-intercepts, of course, are all the roots. So we can go ahead and plot this. So our roots are plus or minus 1 and negative 2. Okay, so this doesn't have to be that big of a graph. Why is this not autocorrecting? Okay, there we go. So let's say we have something like so. I'm going to go ahead and double up the tick marks. Okay, so first I have a root at negative 1, and that's blue. Then I have a root at positive 2, and that's purple. Then I have a root at 1, and that's pink. Did I do that right? Okay, yeah, hopefully I did that right. Okay, so now I know that the end behavior is parabolic, so it's going to do something like so. However, the root at negative 1 is S-shaped. So since I'm coming from above and going downhill, it's going to be S-shaped like so. I don't like the way that looks. Okay, we kind of get the idea. Now, I know I'm going to be coming from beneath the x-axis and going back through the root at 1. And the root at 1 is parabolic, so that means that I'm going to be coming from beneath and making a little parabola. Then I'm going to come around back to the root at 2, which had multiplicity 1, so that's just going to be a little line. Okay, so now I can connect the dots. Oh, let's make my life easier. Where was my y-intercept at negative 2? Okay, so I'm going down to negative 2. That's good. I have all my x-intercepts, so now I can plot using all of this information. So we're going down to negative 2, up through that little S-shaped root. And we're, coming up to this root at positive 1, which is parabolic. So I touch, but I don't go through the axis. Then I come back around and access this root. And then I can, beyond that, let's move these. I always draw these wrong, in the wrong spot, but close enough. Okay, so now let's connect the dots to our end behavior. And there we are. This isn't a guesstimate, a very poor drawing, but hopefully you get the idea. Let's, for fun, see how many turning points there were. 1, 2, 3, 4, 5. So there were 5 turning points. So this is a polynomial of at least 6. And yes, it is a degree 6 polynomial. So I forgot to label this as f of x. So let's make sure I labeled this one as f of x. Okay, let's do another one. So number 3. Let's say we have that f of x is equal to negative x to the 6th, x plus 3 to the 5th, and x minus 2 to the, let's do second. No, I've already got, so let's see, what do I want? Let's do 4. What the heck? Okay. There's something sneaky going on here, and let me make sure I indicate it with a very bright color, and it's this negative. So I've got x to the 6th, then I have x plus 3 to the 5th, then I have x minus 2 to the 4th. Okay, so, oops, I have x to the 6th as a factor, so this implies the root here is 0. Okay, and the multiplicity on the root of 0, of course, is a power, which is 6. So that means that this is going to be S-shaped. Sorry, no, parabolic. What am I saying? Parabolic. What's an even number? That's an even number. Okay. So the next one, let's do the factor of x plus 3 to the 5th. So x plus 3 to the 5th. So that implies that the root is negative 3, which means that the multiplicity on this root, or we have that the multiplicity on this root is 5. So that means at negative 3 it's going to be S-shaped. Okay, last but not least, we have the factor of x minus 2 to the 4th, which means the root is 2. Okay, so that means that the multiplicity on the root of 2, which is the power on that root, is 4, and we know that 4 is even, at least I hope I know it's even by now, so that's parabolic as well. Now there's the caveat, the lead coefficient. So lead coefficient, meaning whatever is in front, is negative 1. So this is going to be reflected, or x-axis reflection. Let me do it that way. X-axis reflection. Okay, what else do we know? The y-intercept is at 0, 0, because when I let x equals to 0, it's just 0. X equals to 0, so that's 0, 0, because of this term here. Okay, so that makes our life easier. So where are my intercepts? Negative 2, 0, and 3. So let's go ahead and draw this x and y coordinate axes. So let's do 1, 2, 3, 4, 5. Okay, so the roots I have are at negative 3, that's a purple. At 0, that's a blue. And at 2, that's a pink. Oh shoot, I forgot to do my overall degree. So, degree is equal to 6 plus 5 plus 4 is 15. So that's S-shaped, right? So let me write this down here. So overall, not overall, end behavior, what am I saying? I don't know what I'm saying. These 60-hour weeks are not doing me well. So end behavior is going to be S-shaped because it's odd, right? Okay, but we have an x-axis reflection, so instead of doing this, we need to be doing this because we're reflected. So therefore, I'm going to come from over here somewhere, and I'll end up going down here somewhere. But what am I going to do in between? So let's look at the root at negative 3, and that is S-shaped, meaning I come down in a little S-shaped graph like so. Oh, I tried to do this nicely, but I can't. Clearly I can't. I don't know why. Why can I not draw this well? Ach, du liebe Scheiße. Okay, so there we go. Good enough for government work, right? Okay, now let's look at the root at 0, which is parabolic, right? But I know I'm going to be coming from down here, from beneath. So I know the parabola is going to be upside down. It's going to look something like so. Little parabola near this root. And then the last root at 2 is also parabolic. So that means that it's going to also look something like so. Okay. Okay, so now I can connect the dots. My intercept was also at 0, so made life easier. So now I'm coming from the left. I go through the x-axis, come back, and I touch the x-axis at 0. My kingdom to be able to draw well. Actually, no, it's okay. I'll keep with my terrible drawings. Okay, so here we are. And then finally, let's see, move this a bit. There we go. So let's see how that looks from far away. Almost okay, tolerable. But hopefully you get the idea. Okay, so this is the graph of f of x. And notice it's going downhill because of the lead coefficient was negative. So let's see, just out of curiosity. We have 1, 2, 3, 4, 5, 6. 6 turning points, so the degree is at least 6. Oh, that's true. The degree is actually 15. So, interesting. Okay, so where was I going to go from here? Okay, so let's note so if the multiplicity of a root is even, then the graph just touches the x-axis, which is the x-axis, with the vertex of its parabolic trajectory. However, if the multiplicity of the root is odd, multiplicity of a root is odd, it cuts through. It cuts through from one side to the other of the x-axis, from one side to the other of the x-axis. Okay, so we can see this was an odd multiplicity here. It was 5, right? However, the other two at 0 and 2, those multiplicities were even, so I just touched the x-axis and I didn't cut through it. Okay? So now let's consider something. Let's consider, what about if the roots aren't easy? Is there any way we can know if there's a root, if it's not a nice whole number? So consider x and y coordinate axes. Let's say we've got a nice function, something like so. Here's my graph of f of x. And let's look at A and B on the x-axis. Pardon me. I know that f of A is negative. So f of A is less than 0. Oops. Oh, I know how to make my life easier. We have new tools. Look at that. Come on, autocorrect. No. There we go. So let's do this one with that same tool. Oh, I guess not. Okay. What happened to the, do I have to change it each time? Wow. Okay. So there we are. I like this tool. I like this. It's really nice. Oh, okay. Well, maybe not so nice. Okay. But now let's go back to up here. We see that f of b is greater than 0. So f of b is positive. And notice that f of x is nice and smooth. It's continuous, right? Okay, so do you agree that there's a point in between? Let's call it C, at which f of c is 0. So if you do, that's good, because there is. If you have a nice, smooth, continuous graph, meaning you can never take your pencil off the graph as you plot it, and you have one part negative and one part positive, you must intersect the x-axis. So we're going to use this fact to find possible, or to note the existence of a root. So this is called the intermediate value theorem. So the intermediate value theorem, intermediate value theorem, so let f of x be a smooth, actually it doesn't even need to be smooth, be a continuous function. Continuous function. Let me be more precise. Let's say over the interval. The interval a comma b. Then if f of a differs in sign from f of b, then there exists some constant c on the open interval from a to b such that f of c is 0. So if we look at our graph, I claim that f of a and f of b differ in sign, right? One's positive, one's negative. So I know that there's got to be some value c, this value here, for between a and b, not at a and not at b, hence the open parentheses, because I know f at a is negative and I know f at b is positive, so I don't need to include a and b in the interval. So C is an element of the interval between A and B. And if it's continuous, I know that there's got to be a C for which the function is 0. Okay, so for example, actually I'm going to use examples from the book. Why don't we do this? So use the intermediate value theorem to show. Okay, so let's do x cubed minus 9x between -4 and -2. So use the intermediate value theorem, immediate value theorem, henceforth the IVT. It's so common that in math we call it the IVT, to show that there exists at least one root, for each of the given functions, for each of the following functions. Kitty snores. Kitty snores. On the given on their respective given intervals. Okay, so number 1, let's say we have that f of x, what was it? What did they have? X cubed minus 9x. So x cubed minus 9x on the interval from -4 to -2. Okay, so we have f of x is x cubed minus 9x, and we have our interval from, oops, am I still doing that? Let's do from -4 to -2. Okay, so let's first evaluate f. Wow, can't even draw an f now. F of -4. What is going on? F of -4. So that's going to be quantity -4 cubed minus 9 times the quantity -4. Okay, so what does that give us? That gives us -4 cubed is -64. And this will be plus 9 times 4 is 36, right? Okay, so what's the difference? If it were 66 that I were subtracting, then that would be an even 30. But it's 64. So the difference between 64 and 36 is 28, -28. Okay, so whatever this is, it's negative, right? It's less than 0. So now let's evaluate. In fact, you know what I should do? I think I'm going to color code all of this. No, maybe I won't. Let's do f now at 2. Sorry, -2. Ugh, really? Okay, these pens are driving me crazy. Okay, so -2. So this will be quantity -2 cubed minus 9 times the quantity -2. So what does this give us? This gives us -8, to which we're adding 18. Okay, well, we can clearly see that that is 10, right? Maybe I should have written this in purple, just so that it stands out a bit more. Okay, so that 10 is greater than 0, right? So therefore, by the IVT, IVT. There exists some constant C. There exists some constant C between -4 and -2, non-inclusive, open parentheses, such that F, let me write F in blue, F at C is equal to 0. Now note, I didn't tell me what the root was, just that one exists, at least one. There could be more, but we know that at least one exists. Okay, so number 2. Okay, let's see, what shall we do? Where are they? Let's do x to the 5th minus 2x between 1 and 2. So x to the 5th, so f of x is equal to x to the 5th minus 2x on the interval between 1 and 2. Okay, so we have that f of x is equal to x to the 5th minus 2x. So let's call the first variable purple and the second variable orange. So we have that f of purple, which is 1, is going to be 1 to the 5th minus 2 times 1. Okay, so this is going to be 1 minus 2. So that's going to be, of course, -1, which is less than 0. So now let's look at f at the orange guy, which is 2. So f of 2 is going to be 2 to the 5th minus 2 times 2. Okay, so that's going to be 32 minus 4. So that, of course, is going to be 28. And that is greater than 0. So because these differ in sign, therefore, by IVT, there exists some constant C, an element of the interval between 1 and 2. Such that f at C is equal to 0. I don't know what that C is, I just know that it exists. Okay, what the heck is going on? Oh my goodness. So I'm a slider, meaning things, electronic things don't like me very much. Okay, so third time's a charm, shall we? So number 3. Okay, eeny, meeny, miny, mo. Definitely not doing decimals. Let's do negative x to the 4th plus 4 between 1 and 3. So f of x is equal to negative x to the 4th plus 4 on the interval between 1 and 3. Okay, so in this case we have that f of x is negative x to the 4th. Now you might say, well, isn't x to the 4th always positive? And you'd be right, except that negative is outside of that power. So let's note. Negative x to the 4th is not equal to quantity negative x to the 4th. So that's the difference. That's why it's still negative. So we want to be careful there. So let's make 1 purple and 3 orange. So if we have, oh, that's weird. What's going on? If we have f to the f of 1, okay, so what's that going to give us? It's going to be negative of 1 to the 4th plus 4. So that's going to be negative 1 plus 4, which is going to be 3,
Yeah.
which is definitely greater than 0. Okay, what's going on? So f of 3 now in, okay, what is going on here? 3 should be orange. So f of 3 is going to be a negative of 3 to the 4th plus 4. So that's going to be a negative. So 3 to the 4th is the same as 9 squared. So that's 81 plus 4. Okay, so I can think of this as a negative of 81 minus 4. So what is 81 minus 4? Is that 77? Well, whatever it is, it's certainly negative, right? So therefore, by the IVT, or by IVT, I know that there exists some constant C between the two numbers 1 and 3, 1 in purple, 3 in orange, such that f evaluated at that C is 0. Okay, so before we go, what I want to note something about this is that the intermediate value theorem does not find the root. So note, the IVT does not locate the root, merely it proves one exists. Merely it proves one exists. Okay, I will see you in the next video.